for today is Andy Magid from the University of Oklahoma, and he'll be speaking on the differential Brauer monoid.
Okay, thank you. It's my first time to give a Zoom lecture, so if the screen goes blank or the sound goes blank, I hope one of the organizers will say something to me. I want to mention that what I'm going to talk about is joint work with Ray Hubler. This photograph that you're looking at, Ray and I are at a VIP reception prior to a performance of the Cirque du Soleil. And this was in almost this time 2 years ago, May of 2019. I met Ray in Seattle in 1968 at a conference. We actually were students together in Berkeley. He got his PhD the same year I got my BA in 1966. But even then, Berkeley was a big place, so we didn't know each other. We met at this conference in Seattle. And then beginning in 1969, when I came to New York, where Ray was at the time, we became friends and colleagues, which lasted, the rest of Ray's life. I want to emphasize just the period of 1969 to 71 when we were first together in New York, and the period in 2019, 2020, when we were again together in New York for periods of time when I was visiting family of mine in New York. In this first period, 69 to 71, Ray and I actually wrote a paper together. You probably don't know it. It seems to have had no citations in the literature yet. It's called Finite Group Schemes Over Fields, and it's a short paper which we published in the Transactions in 1972. It was a paper that we completed, we submitted in 1971. If you're keeping track of those numbers, you know that this year is the 50th anniversary of the submission of that paper. And so we thought, well, it was time to do another one. The subject is differential Azimuth algebras. And what I'm going to tell you is about the work we accomplished there. So just to set some terminology. By monoid, I mean a commutative semigroup with identity. Submonoid is semigroup with the same identity. And U of M stands for the submonoid of invertible elements. If I have a monoid and a submonoid, then I can form the quotient. If N is the submonoid, we say that two elements M1 and M2 are equivalent if there are elements N1 and N2 in the submonoid, such that M1 times N1 is M2 times N2. So this is what you want if the quotient is supposed to have the property that the elements of the submonoid are trivial. That is the identity. So for example, the multiplicative monoid of positive rational numbers contains the multiplicative submonoid of natural numbers, and the quotient is trivial. The submonoid of invertible elements, if you mod that out, the resulting thing has no invertible elements. Now for Azimuth algebras, I thought about taking this as an undefined term, but I also thought maybe we should say a little bit. And the definition I'm taking here is designed to make some other things which happen later on convenient. But just to remind you, in a commutative ring, a projective module is a direct summand, or according to a theorem of Bass, a tensor factor of a free module. So in a parallel way, an Azimuth algebra is a tensor factor of a matrix ring. So as an example, a matrix ring itself would be an Azimuth algebra. And then it's also true, if you think about using this Bass tensor product theorem, that the endomorphism ring of a projective module also satisfies this definition, is an Azimuth algebra. we say that Azimuth algebras A and B are, well, I'm going to call it Brauer equivalent, but this is actually Auslander-Goldman equivalent from their 1960 paper that introduced the notions. The terminology Azimuth came a little later, but we say that Azimuth algebras A and B are equivalent if there are projective R modules P and Q such that A tensored with the endomorphism ring of P is isomorphic to B tensored with the endomorphism ring of Q. And just to point ahead a little bit, you notice that this is very close to monoid submonoid, that if A and B are in some monoid of Azimuth algebras and NDRP and NDRQ are in the submonoid of endomorphism rings, then this is the condition that that A and B are in the same class in the quotient monoid. But anyway, I want to point out that this is a natural definition. Again, referring to result of Bass, A and B are Brauer equivalent Azimuth algebras if and only if they have isomorphic module categories. In other words, Brauer equivalents and Morita equivalents are the same thing. Brauer was actually interested in division rings over fields, but just to comment, if A and B are matrices over division rings whose center is the field R, then A and B are equivalent if and only if the division rings are the same. So now, Azimuth differential algebras are defined here, that a differential, so I'm starting with a commutative ring with a derivation, D, and a differential R module is a R module with a derivation, an endomorphism, which obeys the product rule with respect to multiplication by elements of the ring. And an algebra is differential if it has, well, a derivation. That is an additive endomorphism obeying the product ring and then agreeing with the original derivation on R. So it's an old theorem from the 1970s of Max Knus that every Azimuth R algebra has a differential structure. Now, as Julia Hartman reminded us of, derivations of Azimuth algebras, which are trivial in the center, are inner, and as a consequence, once you have any derivation on an Azimuth R algebra, you have them all. The rest of them are just differ from the given one by an inner derivation. And again, following Julia, there's a canonical differential structure on the matrices. Apply the derivation from R coordinate wise. And that means that every differential structure on the matrix ring is this one plus inner automorphism by a matrix. So my notation for this is to write the matrix ring and then the A, which gives the inner derivation. And just to remind you, of course, the notation means we go from A to a derivation, but there's different matrices could give the same derivation. It's also a theorem that Lourdes Swan and I published in 2019, that every projective R module has a differential structure. Then that means if you start out with an Azimuth algebra, which is an endomorphism of a projective ring, well, you can put a differential structure on the endomorphism of projective module. You can put a differential structure on the endomorphism ring, starting with a differential structure on P. And in fact, every differential structure on the endomorphism ring looks this way, looks like this, because any two of them differ by an inner automorphism. An inner automorphism is an endomorphism of the projective module. You add that endomorphism to the derivation of the projective module, you get another derivation of the projective module. So every derivation on the endomorphism ring of a projective module comes from a differential structure on the projective module. This first theorem here is first result of collaboration with Ray. An Azimuth differential algebra A is a tensor factor of the matrix ring with coordinate-wise derivation for some n, if and only if the Azimuth algebra is actually induced from some Azimuth algebra over the constants. And by induced, I mean not just as an Azimuth algebra, but as a differential Azimuth algebra. And this follows from a result of Lourdes and myself from that same paper I referred to before, that the same property is true for projective differential modules. They're induced if they're, if and only if they're direct sum ends of free modules with coordinate-wise differentiation. Now, a little bit of notation and conventions here, which are going to be unfortunately violated a little bit. So the isomorphism class of an object X of type script X will be denoted with brackets, and the set of isomorphism classes of objects of type X will be script X will be denoted by braces. So the set of isomorphism classes of Azimuth algebras is a monoid induced from the tensor product with identity the class of the ring itself. The isomorphism classes of endomorphism rings of projectives is a submonoid. Then, as I pointed out before, the equivalence relation induced by the submonoid N is the Brauer equivalence, and the quotient monoid, which is denoted BR of R, is called the Brauer group, and it happens to be a group. It's true if we simply look at the isomorphism classes of matrix rings, that's also a submonoid, and the quotient there, which I've denoted BR star, that's also a group. I won't try to pronounce this, it's just BR star. And of course, this group maps surjectively to the Brauer group. Okay, so now we're going to talk about the differential Brauer, well, first group. I'm calling this naive misstep number 1. We look at the monoid of differential Azimuth algebras, isomorphism classes thereof, under tensor product. And we look at the submonoids of isomorphism classes of endomorphism rings of differential projective modules, or the isomorphism classes of differential matrix rings. And we look at the quotient monoids. If we take differential Azimuth algebras modulo endomorphism rings of differential projectives, the differential structure disappears and we just get the Brauer group of R. If we take differential Azimuth algebras, that monoid modulo the monoid of differential matrix rings, the quotient is this BR star of R. I mean, these quotient monoids are groups, but we've lost all the differential. So that's naive misstep 1. Let me introduce a different kind of equivalence of Azimuth, differential Azimuth algebras. Differential Azimuth algebras A and B are said to be equivalent if for some P and Q, the matrices over A are isomorphic to the matrices over B with coordinate-wise differentiation. Now you can think of the matrices over A as A tensor the matrices over R with the coordinate-wise differentiation and vice versa. So another way to think about what we're looking at here, we're taking the isomorphism classes of differential Azimuth algebras, the isomorphism classes of differential matrix rings with coordinate-wise differentiation, both of those monoids, and looking at the quotient monoid. Now, unlike the situation previously mentioned, this is not usually a group. This is what we're going to call the differential Brauer monoid, but it's not usually a group. And this leads to naive misstep number 2. So, well, it's not a group, but let's make it one. K0 as diff of R is the most general group to which this monoid of differential isomorphism classes of differential Azimuth algebras maps. A decade or so ago, Lourdes and I wrote a paper about differential central simple algebras, and we defined the differential Brauer group to be this group generated by the monoid of differential Azimuth algebra isomorphism classes, modulo the subgroup generated by matrix rings with coordinate-wise differentiation. Now, this is definitely a group. It's differential Brauer group, but the elements are not all classes of Azimuth algebras. There are virtual differential Azimuth algebras in it. In other words, there are things that look like fractions. So we back up. To remind you, MDiff is the isomorphism classes of differential Azimuth algebras, and NDiff is the similar thing for matrix rings. The quotient monoid is the differential Brauer monoid. So just for notation here, BM diff of R will denote the differential Brauer monoid of R. And now departing from conventions that I introduced earlier, I want the class braces of A to denote the image of the isomorphism class of A in the differential Brauer monoid. Okay, so to point out these things map to the Brauer group or the BR star, that the first 3 lines in this slide just remind you of what the definition is from the previous slide. I want N1 to denote the image in the differential Brauer monoid of differential matrix rings, and N2 to denote the image of the endomorphism rings of differential projective modules. Then it's a fact that the quotient monoids, well, by the differential matrix rings gives me this BR star of R, that group, and by the quotient by the endomorphism rings of differential projectives gives us the Brauer group of R. So the Brauer group or the BR star group of R are homomorphic images of the differential Brauer monoid, and in fact they are quotient monoids, which can be different things. And then the following, which actually to us was kind of a surprising result, although it's you can see why it's naturality. I'll make some remarks about it. That the invertible elements of the differential Brauer monoid are precisely those which come from this BR star of the constants. And the map here is simply start with a Azimuth algebra over constants and tensor it with R. You recall that this gives you something which is a tensor factor of a matrix ring with coordinate-wise derivation. And furthermore, every tensor factor of a matrix ring with coordinate-wise derivation is of this form. So that's basically the proof of that theorem. But it has another kind of, well, a consequence. If BR star of RD is trivial and the Brauer group of, or BR star of R is non-trivial, then the surjection from the differential Brauer monoid to BR star of R doesn't have a section. I mean, if it had a section, the image of the section would be a subgroup. But if the BR star of the constants is trivial, then there are no invertible elements in the differential Brauer monoid. So this doesn't have a section. This actually has some meaning for us. In other words, there's really no systematic way to choose derivations of Azimuth algebras. I reminded you of Knuth's theorem earlier, which said that there are always, whenever you have an Azimuth algebra over a differential ring, you can find a derivation that makes it a differential Azimuth algebra. And in fact, Ray and I spent some time looking for sort of a canonical way to do this. And well, we have some results, but the bottom line is this: there is no systematic way to find these derivations. I wanted to comment briefly about how to tell when a differential Azimuth algebra is trivial or a differential Azimuth algebra is differentially trivial. To be trivial in BR star means that a tensor or matrix ring is isomorphic to a matrix ring. Julia gave us some good insight earlier about, at least for field diamonds, how to tell when an Azimuth algebra is trivial. To know that they're trivial in BR star, we have to kind of know that they're stably trivial, and this is a slightly different condition. Differentially, so if we have that A is stably trivial, then A has a derivation. We can put the coordinatized derivation on R, and then that means that we get some derivation on MQ of R. And so the class of A is the same as the class of MQR with C in the differential Brauer monoid. I mention this because some of the examples I'm going to turn to now have this, use this feature. So here's the first example. We take R to be an algebraically closed field, characteristic 0, with trivial derivation. So then the quotient BR star as of the differential Brauer monoid is trivial, and so is the BR star of the constants. There aren't any projective modules. So the differential Brauer monoid is just going to be these matrix differential algebras. I'm pointing out here in the first point that if two of these happen to be equivalent in the differential Brauer monoid, then actually the sets of eigenvalues of the inner derivations determined by their matrices coincide. And then eigenvalues of inner derivations are differences of eigenvalues of the matrix that gives it. So if you put these two things together, you'll see that the differential Brauer monoid of this the algebraically closed field with the 0 derivation has the cardinality of C. And then another example, we look at the rational functions over C with derivation, the usual derivative with respect to x. In this case, again, the BR star groups are trivial. In the second case, this is because of the Auslander-Brummer theorem. And then if we take the matrix Z, 2 by 2 matrix, which has a 1 in the upper left-hand corner and the other 3 entries 0, first of all, you can prove that the class of this is, excuse me, not the identity in the Brauer monoid, differential Brauer monoid of C. On the other hand, because there is an element in C of x whose derivative is 1, this class becomes trivial in the differential Brauer monoid of C of x. On the other hand, there are lots of things which are not trivial in the, which we can show are not trivial in the differential Brauer monoid of C of x. In other words, we look at the differential Brauer monoid of C mapping to the differential Brauer monoid of C of x. It's not injective, but the image has cardinality, at least that of C. And then just, so we talk about something which is a differential ring and not a field, and which where there are non-trivial Azimuth algebras. If we take R to be the Laurent polynomials in M variables, and we define the derivation so that D of each of the variables is a scalar times the variables, and we choose the scalars so that the constants are just the field C. Then we're in a situation where the BR star of the constants is BR star of C. That's again a trivial group. So we're talking in a situation where we have no units. On the other hand, BR star of R is a number of copies of Q mod Z. And so this means that when we look at the differential Brauer monoid of R, we have lots of things, you can see countably many things, whose underlying Azimuth algebra is not a matrix ring, and powers of them have underlying Azimuth algebras, which are matrix rings, but none of them have powers which are matrix rings with coordinate-wise derivations. Now, in keeping with the goal that Ray and I had, these results are written as a paper which is available in the archive and kept to a length so that we could submit it to the proceedings of the AMS, hopefully as an 50th anniversary publication. I wanted to close, however, with the following image. I mentioned that at the very beginning, that first picture was Ray and I at the VIP reception for Cirque du Soleil in May of 2019. No, actually, we were super VIPs. We got to go on the backstage tour after the performance, and here we are posing with a couple of the Cirque du Soleil performers, and well, it's a happy picture, and I think that's as good a way as any to end this afternoon. Thank you.
Okay, let's all thank Andy for this beautiful talk. All right, do we have any questions or comments for Andy?
I have a question.
Yeah, just go ahead.
So first, just for understanding, this from BR star to BR, that's an isomorphism if R is a field?
So I'm sorry, could you repeat that?
Just for the Brauer without the differential, just at the beginning, the BR star to BR. If you do that over a field, it's an isomorphism, right? You said it's
Yes.
a subjection in general. Okay, just to make sure I understand this. Okay, and then the other question I had was, so when you normally study the Brauer group, then there are various invariants that people study, like the period and the index. Is there anything that you can do here? I mean, you just showed that this thing is huge, and in particular, it's not torsion. So, are there any analogs of these invariants that one could study?
No, that's an important point. There's no torsion. Well, there's no torsion when there's no units, obviously. So and no units was common to all those situations that I showed you. So there's really there's nothing like that. There the index is raising to a power and to getting some kind of triviality, and that doesn't appear, definitely.
And can it be somehow interpreted as some H2 kind of thing? Or?
Yeah, see, that's another interesting point, that to find something cohomological, you expect a cohomology group. So an H2 is, it's got coefficients in a group. So this is that was one of the reasons that Juan and I stuck to the groups. But the problem with the groups is that we found this explosion of the elements, and kind of inability to actually say that an element of the group was represented by an Azimuth algebra. And so that was where this other approaches led us.
There are some approaches for H2 and kind of non-abelian cohomology. So maybe that would be, and I don't think those are groups. They're just, I don't know.
No, they're not groups. They're pointed sets. But that, yeah, there's so the answer is those are good things to think about. Yes.
Right. Thank you.
Any other questions, comments? All right, so if not, let me thank all the speakers and all the participants of today.